All right, so beta. Beta is where we store our recent history. It's up to H blocks. We store the most recent H blocks. I think H is 8. We do this because when we are receiving work reports, so receiving new work that we apparently has been done from the point of view of the chain, we want to make sure that they're not duplicates. Yeah, it should only be possible to submit the same work report once. Now, work reports have a natural lifespan, which is about H, but within that lifespan, we need to be able to be sure that they're not coming in multiple times, and that's why we keep this recent history. So what do we store in the recent history? Right, well, we've got a sequence up to H elements big. Each element in the sequence represents one historical block, one block from recent history. We store a few things. We store the block's hash, I think that's what this is. We store the recent, yes, we retain its header hash, that's H. We retain its state root, S. We retain its, what we've called its accumulation result, MMR, Merkle Mountain Range. That's this. It's a funny little thing. This is, for what it's worth, how we represent a Merkle Mountain Range. It's a sequence of optional hashes. You don't need to worry too much about that at the moment. It's a pretty simple cryptographic data structure. It's detailed in the appendix. But it basically just details, it's a commitment to a append-only set, right? So you can take a previous commitment, add new items in, and you end up with a new commitment. And the commitment will be to the previous commitments items and the new items that you've added in. Yeah. You can't do that with a regular Merkle root, because you would need to know what items were in order to create a new proof. But you can do it cunningly enough with a Merkle Mountain Range. So that's this. And then also the hash of each work report. And that should be no more than the total number of cores, because we can only process one work report in each core at once. Right? So we have 341 cores. This is a typo. This should be sans serif C. It's good finding all these typos. Right, and that's what this thing is. Right, so this bold P. Generally, I make terms bold when they are sequences or sets of things. The only exceptions to this are where they're fixed length sequences that tend to be considered as one thing. For example, a hash is a sequence of 32 bytes, but I don't make it bold usually, because it's like that sequence, you never add something on, you never remove something. It's considered as just a single quantity. In this case, it's a fairly complex thing. It's like you can have up to C. C is the number of cores, 341, up to C hashes in this sequence. And that's the work reports. Well, specifically, it's the hashes of those work reports. I think technically it's actually the hashes of the work packages in the work reports, but we will find that out very soon. So during the accumulation stage is when we populate, when we do most of the change, when we do most of calculating beta prime, the posterior beta, from the prior value. We do one thing at the beginning, though, sort of earlier on in the block. One thing that we can very easily do, and that is that we set the state root of the most recent historical block. So this So beta dagger, you'll see this construction quite a bit in the grey paper. Beta dagger is exactly the same as beta, except that beta dagger, the first entry in beta dagger, which is the most recent historical block, S, the state root, the posterior state root of the most recent historical block, we set that to our prior state root that we now know because it's fed in. We didn't know this at the point of time of processing the most recent historical block, i.e. our parent block, because we only get given the prior state root, not the posterior state root. If this were a chain like Ethereum or Polkadot, where we get given the posterior state root in the header, then we would be able to fill this in immediately. But we only know the prior state root. And therefore we have to wait until the next block before we can fill this thing in. So we fill it in as soon as we know it, which is presumably at the beginning of the block. After that, we get this intermediate value beta dagger. We then transition, we can take beta dagger and calculate beta prime, the posterior beta, once we know a few other things. Basically, once we've worked out what work packages are coming in this block. We only know that when we've looked at the extrinsic that's telling us which work packages are going to be processed, like which work reports are coming in. Now, I haven't explicitly said this so far, but I will say it. I think actually maybe I have. But anyway, a work package is a packet, like a bunch of work to be done. It's a piece of work that gets done, that gets fed in to one of these orange segments. Yeah? And then the boundary between this orange segment and the reactor core, the on-chain part, that's the work report. The work package never makes it out of the other side of the orange segment. It's too big. Work packages are big. Like, there's a lot of data that goes into work packages. It would be way too big, way too much to feed them all into the reactor core. So that's why we have this pre-processing stage. It's sort of like a distillation stage. It does all the computation and it results in a much smaller work report. It's sufficiently small that it can actually, all 341 can make their way into the reactor core and then get reacted together in the state. Yeah? So that's the difference between a work package and a work report. Work package implies there's some work to be done. A work report is, with the work having been done, it's like the results of the work. And there's a few other bits in there as well. Right, so we're wanting to know what the hashes of these work packages are, so that if anyone tries to put a work report in that's already of a work package that's already been submitted, then it will fail. Like, we want to prevent this from happening. So we take beta dagger and we append onto it a few things. First, the state root. Well, we don't know it yet. Yeah, this is our current block. We only know the prior state root. We don't know the posterior. So we just fill it. It's just a hash of zeros. That's how it's defined for the moment, right? So the most recent historical block will have a hash, a posterior state root of zeros, because it's our current block and we haven't yet actually done the work, right? We don't know what it is. Like whoever is creating the block, they've worked out what work they have to do. They've committed to doing that work, but they haven't actually done it yet. They don't know what the posterior state root is, and therefore it's all zeros for now. In the next block, that will get set. And that's what this bit here does. But we can't do that until the next block, when we've actually worked out what the ramifications are for the work we've committed to doing. What else have we got? H, hash of the header. That's easy. We already know that. That's our commitment. B, that's our Merkle Mountain range, which is essentially a commitment to all of the things that have happened so far in Accumulate. In basically all of the stuff everything that has been fed into the reactor, it's allowed to basically emit a bit of data from that reaction, in addition to changing the state. And this all gets fed onto that Merkle mountain range. And this allows proofs to be created that some particular thing made its way into the reactor, or indeed some particular reaction happened. Yeah, something happened in the reactor. It turns out this is very useful for making proofs of important things into systems like Ethereum. So let's, right, that's what these two things basically say. A is the append onto a Merkle mountain range function. And what we do is we take the last, hold on, let's have a look. Right, so we're going to take the empty sequence, and on that empty sequence, add all of the last beefy, that's what this is about really. If you're familiar with beefy, that's what this protocol is. All of the last Merkle mountain ranges. And if it turns out there are none, if it's the first block, then it's just empty. We just got the empty sequence. And we take the last of these, the last one of these, and then we feed that into our, we append that onto our Merkle mountain range. R in this case is a Merkle tree. It's a basic binary Merkle tree. Nothing special about this. It's not our state Merkle tree. We're using the Ketchak hashing scheme. And we care about C is actually the output of the accumulates. So it's basically all of these reactions that happen in the reactor core. They may result in a datum, in the sort of they may yield some data, a hash basically, and that's what this set C is. We don't define it yet because we define it in accumulate, which is going to come later, but it's just defined in section 12, but we're gonna pretend that we know it for now. And it's all of the things in C. We're going to encode them. We're going to order them. That's what this squiggly line means. And then just take them, make a sequence out of them, turn that into a Merkle root, and that's R, our root. And we're appending R, our new root, onto the previous bunch of roots, our B bold from our last beta. Yeah. So the interesting thing here is that, yeah, of course, right. So we take our last beta, we pull out the Merkle mountain range from it, and then in case it's empty, which it shall only be empty if it's the Genesis block, but we have to make it work in that case. We basically stick this, we prepend this empty sequence, which is the empty Merkle mountain range, and when we take the last of them. So this whole expression here is basically just saying, take the last Merkle mountain range, but in case there was none, start with an empty one. Yeah? And then append this new root onto it. And that's our new Merkle mountain range. That's what these two things are saying. Okay, then we've got P. So P is, if you remember, it's the hashes of the work packages that we are processing in this block. First, we go through our reports that are coming in, our work reports, one for every core, or at least at most one for every core. In general, there should be one for every core. And we are going to extract the work package from it. It turns out that it's a bit deep into the data structure as it's formalized here. So it's the guarantee, the sort of report guarantee. We take W, which I think is the work package, and then we take S, which is the data specification of that work package, and then we take W is the work report, S is the data specification of the work report, and then P is the package hash of that inside of that data specification. It doesn't really matter, but that's what this huge sort of deep expression here means. GWSP just means the work package hash of the work report G. And that's basically it.